A billiard ball is a solid sphere with a diameter of that. So underline diameter, because we'll probably want radius, 58 millimeters. Suppose that a billiard ball is placed on the table and hit perfectly horizontally with a cue stick so that it has no spin. So the pool cue is not imparting any torque on the cue ball. If the coefficient of friction between a ball and the table is mu k, where coefficient of kinetic friction is 0.15, then what is the angular acceleration alpha of the ball just after it is hit? For the limit check, investigate what happens to alpha, the angular acceleration, if the table becomes quite slippery, i.e. mu of k approaches 0. Okay, so first thing to do, draw a picture, because that's pretty much what we always do. Have a cue ball, and it's on a table. I guess I should use green for the felt. And it has some force going that way. And that's not what we're going to be concerned about, because what we're going to be looking at is force friction going this direction. All right, so from here we have we're concerned with angular acceleration. So angular acceleration comes from torque. Torque is moment of inertia times alpha. Alpha is the angular acceleration. Another definition of torque, so this is basically Newton's second law. So we have F equals ma, but instead of mass, we use moment of inertia. Instead of acceleration, we use angular acceleration, basically the angular equivalent. So also, torque is the angular equivalent of force, so that is going to be equal to R cross F. And these should all actually probably be vectors. So R cross F, R is going to be the distance from the center of mass to where the force is applied. In this case, it's going to be force friction. And this cross product is a measure of how perpendicular two vectors are. And so if R is straight down, force friction is straight back, then these are perfectly perpendicular. Sometimes people will say that cross product is the sine of the angle between the two vectors. So since these are perpendicular, it's going to be a sine of 90 degrees, or pi over 2 if you like to use radians, which is just 1. So R cross F is just going to be RF times friction. All right, so now we got this part. We want to find angular acceleration. I think I'll go one step further. I'm going to say that moment of inertia, if we look this up, go to Wikipedia. We'll do list of moment of inertia. Scroll down, and we could derive this. We're not going to derive this. So it's based on the geometry of the shape that's rotating. So in this case, we're going to have a solid sphere of radius r, mass m, and that's what's going to be rotating here. And so this is going to be moment of inertia 2/5 mr squared. And it's going to be rotating. Its axis of rotation is going to be about the center. So 2/5 mr squared, I equals 2/5 mr squared. And then force friction, that's going to be the coefficient of kinetic friction times force normal. In this case, we have force gravity going down, force normal going up. And so force gravity is going to be the same as force normal, opposite direction. And so we're going to have coefficient of friction K times mass times gravity. All right, so now we can put it all together. I'm going to use this equation right here. I'm going to solve it for alpha. So alpha equals R force friction over moment of inertia. That's supposed to be an I. Moment of inertia of this sphere specifically. So we're going to have R mu K mass gravity all over 2/5. So when we divide by 2/5, that's the same as multiplying by the reciprocal. So 5 over 2 times mass times r squared. Do a little canceling. One of the r's will cancel out. The mass cancels out, which is good because they don't give us what the mass of the cue ball is. And we get 5 mu k times gravity over 2r. From there, we go to Wolfram, calculate it out. Wolfram. And this is going to be 5 times coefficient of friction, I think that's 0.15, which seemed reasonable. Yep, 0.15. And the radius is going to be 29 times 10 to the negative third meters. We want it in meters, and we had to divide by 2 because they gave us a diameter. We wanted a radius. Though I could have just called 2r the diameter. That's okay. I'm not that clever. I am not going to do that. 2 times 29 times 10 to the negative third. And this should give us an angular acceleration. 5 times 0.15 times 9.8 divided by quantity. 2 times 29 times 10 to the negative third. Seems like quite the spin, which is going to be 126.7 radians per second. Maybe squared, because it's a angular acceleration. Now, that's its initial angular acceleration. Once it starts rolling, it's going to be reduced. So even though you get a crazy high number here for the acceleration, it doesn't maintain that acceleration. That's why they ask for the acceleration just after the ball is hit. All right, and so then it says, for the limit check, investigate what happens when alpha when mu of k goes to 0. So mu of k, right here, when that goes to 0, then the whole numerator goes to 0. Numerator goes to 0, the whole fraction goes to 0. So limit as mu of k goes to 0 of alpha is 0. Alpha also goes to 0. So basically that makes sense. Because if it's going to slide, there's going to be no friction to cause it to spin. So that's what would happen if your kinetic friction lowers. So kind of backtrack, look what we did real quick. First thing we did draw a picture. We wrote up 2 definitions of torque. One, moment of inertia times angular acceleration, and the other one, r cross F, which is the moment arm, r, cross the force friction. And since they were perpendicular, we just basically ignored the cross product. Cross product is a measure of how perpendicular 2 vectors are. They're already perpendicular, so we use the total magnitude of both vectors, r and f. So, or you can think of it multiplied by the sine of 90 degrees, which is 1. Rearrange things, put in some values, looked one up, and got an answer. So, hope that helped. See you next time.